everyone. I'm so glad you could join us for one of my favorite sections that we're going to be revising today, and that is geometry. So grade 12, it's a huge part of your paper 2, and I also know that it's one that many learners do not like, and I understand why. It's very hard to understand which theorems need to be applied and when you need to apply those theorems. But what I can advise you to do when it comes to geometry, and I know I say it with all of maths, but geometry especially, is a lot of practice. It's also a very logical section. So if you've made a mistake previously, you're not going to be able to carry on and prove other parts of the question because the mistake will be carried through to the remainder of the question. So it's a very, very logical section. If you do things correctly, the logic will follow through. Okay, we're going to go through some of the hints and tips to help you pass the geometry section of your exam, but it is one that I know is a tricky one. So one of the other things you can do is make sure, like you have a directory or you have a collection of your best friends and that, and you keep their numbers, maybe you learn them off by heart. In geometry, when it comes to the theorems that you need to keep it in a little special medical bag where you can just pick them out as you need them, your little maths toolkit, we call it, and you can pick each theorem as and when you need it. So if you want to know when do I use each theorem, the only way you're going to know that is firstly by learning all of your theorems. So that's all of the grade 11 stuff and all of the grade 12 stuff. You need to know all of your theorems and you need to know when to apply them. How do you know when you need to apply them? You need to do lots and lots of questions. Okay, now when it comes to an exam as a whole, and it really, this works for every subject, you need to break it down. So in other words, don't try to learn an entire subject in one go. You need to divide each subject into manageable sections that can be covered in an hour. It's usually not advisable to study for more than an hour at a time because your brain becomes quite tired and it starts getting bored and it cannot absorb enough information. So have a break between each hour before you continue to the next section of work. So for example, when we're talking about maths, you aren't going to study, okay, today I'm just going to do maths and then go from paper 1, all of paper 1, all of paper 2. That's not advisable. You can take one section of work. So for example, take the section geometry, and then you can decide, okay, well, today I'm going to learn geometry for paper 2, or you can look at learning analytical geometry or statistics or trigonometry. So don't try and put them all together and learn it in one big bunch. Just break them up. Even those sections themselves can be further divided. So when you're looking at analytical geometry, you can look at dividing that into circles and tangents and other little sections so that it becomes more manageable to deal with. All right? Easier to learn. Now the CAPS breakdown for your geometry part of your exam, well, Euclidean geometry and measurement, that accounts for 50 to 53 marks. That's massive in paper 2. That's approximately 33% of the final exam. So you cannot hide away from geometry. It will find you. It's 30% of the exam. Some of the things, and just a checklist for you guys to go through as you start learning geometry. Obviously, make sure you learn proofs of the following theorems, okay? So you need to know the theorem, the line drawn from the center of a circle perpendicular to a chord bisects the chord. That's grade 11 work. The angle subtended by an arc. Okay, so all this stuff that we're talking about now, circle geometry, grade 11 work, you need to revise all of that. The angle subtended by an arc at the center of a circle is twice the size of the angle subtended by the same arc at the circumference of the circle. All right, and that's always on the same side of the chord as the center. That's what we call the angle at center theorem. You also need to learn the theorem, the opposite angles of a cyclic quad are supplementary, so they add up to 180 degrees. And the angle between a tangent and the chord drawn from the point of contact is equal to the angle in the alternate segment. This should all be old news to you, and you should understand each of them already. Okay. Now you must understand the application of the following. So these are what we call corollaries. They derive from the theorems. We also call them axioms. Okay. You need to know about angles in a semicircle. Remember, angles in a semicircle are equal to 90 degrees. Also, equal chords subtend equal angles at the circumference, and equal chords subtend equal angles at the center. In equal circles, that means they have the same center and the same radius. Equal chords subtend equal angles at the circumference. In equal circles, equal chords also subtend equal angles at the center. The exterior angle of a cyclic quad is equal to the interior opposite of a cyclic quad. So that's, again, circle geometry. If the exterior angle of a quadrilateral, so this is now the converse of the previous one. If the exterior angle of a quadrilateral is equal to the interior opposite angle of the quadrilateral, then that quadrilateral must be cyclic. So that's the converse of the previous one. Tangents drawn from a common point outside the circle are equal in length. That's important because it then forms an isosceles triangle. All right. Obviously, this is knowledge of geometry from previous grades will be integrated into questions in the exam. In grade 12, you also learn about similar triangles and similarity. You need to understand how to prove triangles similar as well. All right, and that can all be integrated into one question. So you can have similar triangles within a circle. So you need to understand your circle geometry as well. Okay. Now, importantly, if you have attempted to answer a question more than once, and you know this does happen sometimes, guys, you realize you've made a mistake and that one didn't make sense, you go and what do? You need to make sure that you cross out the answer that you do not want marked. If you don't do that, this is very important. If you just leave all these options for the examiner to choose from for 10.1, you've got maybe 3 different versions, they're only going to mark the first one, and maybe your last one was the one that you really wanted marked. So anything you don't want marked, you need to put a line through it. All right. You must learn proofs of the theorems. However, the converse of the proofs will not be examined. You need to understand what those converses say, but you won't be asked to prove a converse theorem. Okay, so the best way to learn geometry is to do geometry. So this is the first question for today. This comes from the DBE November 2015. It's question 8.2, Maths Paper 2, of course. I'm going to give you some time to really, what I'd like you to do, because you need to have this diagram, take down the diagram, mark down the information that is given to you. So don't start writing now in the diagram below CDs. It's going to take too long. You're not going to have enough time to take the diagram down. So the main thing you need to do now, take down the diagram and write down the key information on the diagram. All right, I'll give you 3 minutes to take this down. Okay guys, so I hope that you've got all the information down. That was the main thing. Get the diagram down, get the information that you need in those 3 minutes that I gave you. Okay, let's read through the question. I find the best way to do geometry is to read the question, and as you read, put down any relevant information from what they tell you. Put that down straight away into your diagram. In this question, they actually don't say much. They tell you that in the diagram below, CD is a common chord of the two circles. Straight lines ADE and BCF are drawn. Okay, well, we can see that they're drawn. Chords AB and EF are drawn. So chords AB and EF are drawn. So we've got a whole lot of chords and lines. So they don't really say much. However, just from the drawing itself, you can already start seeing some things happening. And if I look at the bigger circle with the quadrilateral ABCD, I can see that those 4 points lie on the circumference of the circle. So those vertices are on the circumference of the circle. Therefore, ABCD is a cyclic quad. I can see that just by looking. And then in the little circle, CDEF, those points are also on the circumference of the little circle. So therefore, CDEF is a cyclic quad. And that will definitely be enough information to help you prove that EF is parallel to AB. Now, when they start asking you things like this, prove that EF is parallel to AB, you need to now have enough knowledge in your geometry toolkit that you can draw on so that you can say, well, if I need to prove lines are parallel, what options do I have? And to prove that lines are parallel, you have to prove either they are co-interior angles, alternate angles, or corresponding angles. That's the main thing. That's the first thing I look for. There's different ways to prove lines are parallel depending on the question, as you'll see in a later example. But in this specific question, just given the two cyclic quads, I'm going to draw on that information. Corresponding co-interior alternate angles. Can I find them in this diagram? So we start out our proof like this. We're trying to prove that AB is parallel to EF, and I look at the information that I've been given and I can make the following statement. I know that angle C1 is equal to angle E. How do I know that? Well, that's the exterior angle, C1, is equal to angle E, and that's because angle C1 is the exterior angle. Okay, and I'm going to abbreviate quite a bit here because I don't want to run out of time, of cyclic quad CDEF. Okay, so I know C1 is equal to E. I also know that angle C1 plus angle A is equal to 180 degrees. How do I know that? Angle C1 plus angle A is equal to 180 degrees. Well, I know that because I've learned my theorems, and I know that that's opposite angles of cyclic quad, and you can name it here again. We're dealing with ABCD. Opposite angles of a cyclic quad are supplementary. If you don't know your theorems, you are really going to struggle with geometry. Okay, you've got to learn them. All right, so what is the aim here? Well, my aim is to show that angle A plus angle E is 180 degrees. Because if those add up to 180 degrees, well then AB would have to be parallel to EF because A and E would be co-interior angles. Do I have enough information to make that statement? Well, yes, I do. Because I know that C1 is equal to E, but I know that angle C1 plus A is equal to 180. Therefore, I can just replace angle C1 with E. So I get that angle E plus angle A is equal to 180 degrees. And these are, so then you say, therefore, if E1 plus A is 180 degrees, then that means that AB must be parallel to the one that they've asked us to show, EF, because those angles, E1 and A, would then be co-interior angles. Co-interior angles supplementary. So therefore, those two lines must be parallel. All right, a nice easy geometry question, I think, to start us off. Obviously, we're going to look at harder ones as we get into the lesson. So stay tuned, come back after this. Welcome back everyone to our revision, our geometry revision section, and we're looking at questions from past papers, and we're looking at how we apply the theorems that we already know from both grade 11 and grade 12 geometry, all right? So in the next question, this comes from the DBE June-July 2015 paper. This is question 10, and obviously we're dealing with maths paper 2. And what I'd like you to do is to first complete question 2.1 on your screen. It's a very, very quick one, and then I'm going to give you a chance to take down the drawing of question 2.2 and to fill in as much information as possible. So start thinking, get your brains thinking about how to solve question 2.2, but the main thing is get the diagram down, get the information into the diagram. I'm going to give you guys 3 minutes for this. So everyone, here we were really testing that you understand the proportion theorem. So in the first part of this, really just completing the statement where we say, if a line divides two sides of a triangle in the same proportion, then the line is parallel to the third side of the triangle. Okay, that's 1 mark, and you all should have gotten that easy 1 mark. Okay, the next one, which is application of that theorem, we're told that in the diagram, triangle ABC is a triangle with F on AB and E on AC. That doesn't really give us much information. However, the next part does. It tells us that BC is parallel to FE. So BC is parallel to FE, and you can see that that's marked on your diagram. And D is on AF with AD, so they give you that AD over AF is in the ratio 3:5. Now guys, please remember, don't make the mistake of thinking that that means that AD is 3 units and AF is 5 units. It just means that that is the ratio of these two sides. So AD over AF is 3/5. It's not actual values, all right? They tell you that AE is 12 units. Now that is an actual value, 12 units, so that's marked on your diagram. And EC is equal to 8 units. Okay, great. So just looking at the diagram, so what I like to do is look at the given information and already start deciding for myself, well, what does the given information tell me before I look at what they want me to prove? Because I can see that side FE is parallel to BC, I know that I'm going to be able to use the proportion theorem in triangle ABC, and I'll be able to say that AE over EC, side AE over EC, is equal to side AF over FB. So those are kind of things that I already start thinking of, and we then look at the question and see what it is that they ask us. They say, prove that DE is parallel to FC. Okay, so let's just erase that for now. So we want to prove the ones that they didn't give us, which is DE, those two sides. DE is parallel to FC, and they didn't tell you that. So you've got to start thinking, well, what are the ways that I can prove that that is parallel? Now, some of you will start going with alternate angles and corresponding angles and all of that. Remember, you've got to use the theorem that's applicable, that's relevant to the question that you've been given and that you can see in the easiest way. So if you're trying to find corresponding angles because you saw another pair of parallel lines or alternate angles, it's going to be very tricky. You need to work within the concept that they are testing, which is proportion. It's going to be a much easier way to get the answer out, all right? So to prove that DE is parallel to FC, for me what that means is I need to show that side AE over side EC is equal to side AD over side DF, or in fact any of the proportions there. They gave you what did they give you? They gave you AD over AF. So they went, just going to erase this so you can see more clearly what we're talking about. They gave you the ratio AD over AF. So for me to prove that DE is parallel to FC, I want to try and show that side AE over side AC is in the same proportion as the sides they gave you, AD over AF. So it must be equal to 3/5. If I can show that, then that means, well, that's then the converse of the proportion theorem, because that means the line will then divide that triangle in proportion. Okay, so let's try that out. So if we look at side AD over AF, just writing that down, they gave you AD over AF. They told you that that's 3/5, all right? So AD over AF, if I look at now AE over AC, and let's look at what ratio we get there. Well, we see that line AE is 12 units, and AC, which is made up of the two segments AE and EC, is going to be the sum of AE and EC. So therefore AC will be 20 units, 12 plus 8. I can then simplify that a little bit further. 4 goes into 12 3 times, and 4 goes into 20 5 times. And look at what we've shown. We've shown that the ratio of AE over AC is the same as the ratio of AD over AF. So that must mean that those two lines, which they want us to prove, are in fact parallel. So therefore AD, so we set it up like this, over AF is equal to AE over AC. Therefore, DE must be parallel to FC, because the line divides the triangle in proportion. So it's really just the converse of that theorem. So because what we're saying is, because these lines DE divides this triangle AFC, so if you look at AFC, it divides that triangle in proportion, it must mean that those two line segments DE and FC are parallel. All right. Okay, so for the next one, they now give you units to work with. They say that AB is 14 units. So AB, which is that length there, that's 14 units. They're asking you to calculate the length of BF. So what are we going to use here? Now remember, you've also got, and you were given, that side FE was parallel to BC. So that implies that you can use your proportion theorem in triangle ABC, okay, in the following way to help you work out the length of BF. So I'm going to have to keep going backwards and forward so that you can see the diagram as we go through the question. So this is 2.2.2, I think it was. Yep. So you're told that AB is 14. So I can say, well, AB over FB is equal to side, the same ratio, AC over EC, and that's the proportion theorem. We can say, well, side FE is parallel to BC, or we can just state proportion theorem. All right. So therefore, AB over FB is equal to AC over EC. We've got some values that we can put in there. AB is 14, so I can replace AB with 14. And AC is 20. EC is 8. So that means I've got a little equation now that I can solve. So you can cross multiply. So that's where you multiply the numerator on the other side of the equation with the denominator on the left-hand side. So we get 20 times FB is equal to 14 times 8. All right, and then we'll divide both sides by 20 to get the length FB. Okay, so let's have a quick look at what we get there. So we've got 14 times 8 divided by 20, giving us 5,6 units. All right. Okay, guys, so this is really just an application of the proportion theorem. Not many of you would have battled with this, but it does test that you understand how the theorem works both conversely and then a straightforward application of that proportion theorem. All right, I think it's a good time for us now to take a break before we continue with the next Euclidean geometry question. We're back after this. Welcome back, everyone. So far, we've been looking at geometry, and what we've looked at is a question involving the proportion theorem, and then we also looked at, before that, we looked at a question involving just a cyclic quad and circle geometry. So now this next question comes from the November 2015 paper. It's question 9 for those of you who are revising from past papers. For those of you who don't have past papers, I'm going to give you a chance to take the question down. Again, very importantly, the main thing you want to get is the drawing. Get the drawing down. We'll fill in the information as we go. All right, I'm going to give you 3 minutes to take this question down. Well, with these type of geometry riders, what I always like doing is having quite a few different colors of pens around so I can mark down given information. If you don't have many different colors of pens, you need at least a pencil and eraser and an eraser. Those are essential tools for answering geometry questions. You have to have a pencil and an eraser so you can mark down given information. All right. So let's read through it. We've got that in the diagram, triangle ABC is drawn to the circle. TA and TB are tangents to the circle. Before I even carry on reading the remainder of that, I mark off what that tells me. If TA and TB are tangents to the circle, they must be equal because tangents from a common point are equal. All right, so that already starts leading me to other information and other equal angles. So for example, just from that given information, as we go on, we'll be able to mark down more things. They tell you that the straight line THK is parallel to AC. So we've got that TK is parallel to AC. That's drawn as well. Obviously, that's going to tell us a lot about our angles. And H is on BA and K is on BC. So H is on BA, so that's that chord going from the point B to A, and K is on BC. Don't get much information from that. AK is drawn, and they say let's angle A3 equal to X. So already before I look at what they want me to prove, I can start seeing things. I can see, well, if TA is equal to TB, because those are tangents from the same point, and A3 is X, that must mean that angle B2 is also X, because triangle TAB is isosceles. Okay, so that's just information I can mark down. What else do we know? Well, they've told you that AC is parallel to TK, so that means you're going to get corresponding angles, alternate angles, and all of those forming. So we don't have enough information with X yet to mark down other angles, but as we go into the question, we're going to see what it is that they require. All right. Also, given the fact that TA and TB are tangents, you can use the tan chord theorem. The tan chord theorem tells me that angle TAB, which is angle A3, will be equal to the angle in the alternate segment. Now, to find that one, you draw a chord, all right, and then you follow that chord to where it's going to take you onto the circumference of the circle. So BA, if I follow that chord, that takes me to angle C. So from the tan chord theorem, I'm going to get that angle C is equal to X. All right. So those are things that we can just start marking down on our diagram. That's not really going into any proofs yet. But what that does is it starts our brains thinking along the line of geometry and then just going over the theorems already that we may possibly need to use. Okay, so I always find that that's helpful for me as a starting point. I then go and read the question, which the first one says, prove that angle K3 is equal to X. Well, already just in our discussion in marking down information on the diagram, I can already see a clear route to proving that angle K3 is equal to X. Let's have a look at the diagram. So K3 being that angle there, all right? I know that angle K3 is going to be equal to angle C. How do I know that? Well, you've got that TK is parallel to AC, so K3 and angle C are corresponding angles. So if only I knew that angle C was X, that would mean that angle K3 is X. And I do know that angle C is equal to A3 because of tan chord theorem, so it's also equal to X, all right? So therefore, I can say the following to set up my proof, and it's also important to remember how you set out your proof. So the first thing we're going to say is angle C is equal to angle A3 is equal to X. And remember in geometry, if you make a statement, you need to give a reason. So why is angle C equal to A3? That's the tan chord theorem. Okay. I also know that angle C is then equal to angle K3 because those are corresponding angles. And you can list your parallel lines, but to save time, I'm not going to write them down. So C is equal to K3. Therefore, you must get that since angle C is equal to x, and this is the logic that comes through in geometry, if C is equal to x, but C is equal to K3, that must mean that K3 is also equal to x. So therefore, angle K3 is equal to x. All right, and that just follows. It's a straightforward reasoning. Okay, so now that we've marked that down, let's move on to the next one. The next question says, prove that AKBT, so that quadrilateral, is in fact a cyclic quadrilateral. So what that means is that if you were to draw a circle around those 4 points, AKBT, those 4 points will end up on the circumference of the circle, all right? Now, the ways at your disposal that you have to prove that a quadrilateral is a cyclic quadrilateral, you can either prove that the opposite angles are supplementary, exterior angle of this quadrilateral is equal to the interior opposite, or you can prove that the angles on the same side of the chord are equal, which is the converse of angles in the same segment. The one we're going to go for, and it's just glaring at me, if we look at at the quadrilateral AKBT, so that's that one there, we can see just from what we've proved that angle A3 is equal to K3, but those are angles in the same segment. So that must mean that this quadrilateral AKBT is a cyclic quad. All right, so you see how one part of the question leads into the next. So we can say, well, angle A3 is equal to angle K3, and that was actually just proved previously, or you can say because they both equal x, therefore, AKBT is a cyclic quad. And your reason, remember, if you make a statement, give a reason, it's the converse of angles in the same segment. All right, converse of angles in the same segment. Or you can actually state that whole converse if you prefer. All right, let's quickly move on to 3.3 now, where we are told to prove that TK, line TK, bisects angle AKB. Okay, so on our drawing, and let's just once again get rid of what we just put in so we have a clearer picture of what's happening. Okay, so you've got X and you've got X here, and the only reason I'm erasing it now is just so that it's clearer to you, but in an exam you want to keep all that information there. We want to prove that line TK bisects angle BKA, sorry. So what you're trying to prove is that angle K2 is also equal to x, because if angle K2 is equal to x, since K3 is equal to x, that means that the line TK bisects angle BKA. All right, so how do we prove that angle K2 is equal to x? Well, there are different ways to do it, and this is also the nice thing about geometry. There's not just one straightforward way to get to the answer. There's different reasonings to get you to the same point. So the one that I'm seeing that leaps out at me is that angle B2 is equal to x, either because of the isosceles triangle TAB, or if you want to use tan chord theorem, angle B2 is equal to angle C, which is x. And then since we've just proved that BKAT is a cyclic quad, that means that angle B2 will be equal to angle K2, which is equal to x, and therefore line TK bisects that angle BKA. All right, let's write it down. And this is always the tricky part, because you want to sort of translate what you did on the diagram into words, and a lot of people get stuck here. So let's go through this. So we want to start by saying why is K2 equal to x? So that's where our reasoning needs to start. So I'm going to say angle B2 is equal to angle C is equal to x because of tan chord theorem. Or as I said to you, you can use the isosceles triangle formed by the equal tangents. All right, but we know that angle B2 is also equal to angle K2 So that's also going to be equal to x because we've proved above, proved that AKBT is cyclic. So these will become, so since we've proved that, these two, B2 and K2, will be angles in the same segment. All right, so B2 is equal to K2 is equal to x, and therefore we've got that angle K3 is equal to angle K2, which is equal to x. So we can say, therefore, line TK bisects angle, and how did they say it? They said AKB. So bisects angle AKB. Okay, since both K3 and K2 are equal to x. All right, guys, so far we've got quite a lot of information on this drawing. That's why it's important to make sure that you are following logically and you're getting the right steps logically, because as you can see, once you make a little mistake in geometry, it can throw off the questions that follow. All right. So part 3.4 very quickly says that prove that TA is a tangent to the circle passing through the points A, K, H. So prove that line TA. All right, and I'm going to again erase these lines, but simply because it's going to be easier for you at home to see without those lines. But generally, in a geometry exam, you want those markings there. That's the one we've just proved now. So we want to prove, again, that was TA is going to be a tangent to a circle passing through the points A, K, H. So in other words, if you could get a circle and draw it around those points, all right, then you want to prove that this line TA would be a tangent to those points, all right? So mine is not quite a circle, but what we're saying is in order to prove that, we would then need to imagine if in fact, we could draw a circle around those points, and if TA were to be a tangent, that would mean that the angle A3 would have to be equal to the angle K2, because that would be the tan chord theorem, all right? So we really use converse logic here. So to prove that TA is a tangent to that circle, we'll say, well, we've already shown, this is 3.4, we've already shown really that angle A3 is equal to angle K2, and that was because they were both equal to x. We've seen this already, so they're both equal x. So therefore, line TA would be a tangent to circle AKH, and the reason for that, well, that's the converse of tan chord theorem. So what we did there is we showed that the angle between the tangent and the chord would be equal to the angle in the alternate segment. So we've worked conversely. So if that is in fact the case, that must mean that TA would be a tangent to the circle you could put around those points. We've got one more to do. Let's go through it very quickly. I'm probably not going to have time to write down the proof, but I just want to go through the logic with you. They tell you that S is a point in the circle such that the points AS, KB are concyclic. So AS, KB, concyclic means it's a cyclic quad. All right, so those are concyclic. And they then say, you need to explain why ASBT would also then be concyclic. So let's quickly get another color. We've got ASBT, so going like that. Say why that would be concyclic. Well, just from the drawing, and it is quite an untidy drawing, but what you can see is that this angle, because quadrilateral ASKB was given to now be a cyclic quad, we can say, well, this angle S is going to be equal to 2x because of angles in the same segment. All right, so if you follow chord AB, you will see that in cyclic quad ASKB, angle S is also going to be 2x, or angle ASB, all right? But we also know that angle T is equal to 180 minus 2x. You can use angles in a triangle to show that. So therefore, what you're going to end up with is angle ASB, angle ASB plus angle T is equal to 180 degrees, but then those angles are opposite angles in the quadrilateral that are supplementary, so that means using the converse, since the opposite angles of this quadrilateral are supplementary, the quadrilateral must be a cyclic quad. All right, guys, that's it for today's lesson. We went through quite a lot of information on how you could pass geometry with a better mark, and I hope you found today's lesson very useful. Until the next time, cheers.